Hi, my name is Aisha Muhammad Ali and my student ID is 108757.
Hello, my name is Benicia. My matrix number is 109194.
Hi, my name is Brian Hugh Anak Kelvin Jackson and my matrix number is 107891.
Hello, my name is Ibeli Marcia with the matrix number 109846.
Practical 1 is about spectrophotometry. Spectrophotometry is an analytical technique that measures how much light a substance absorbs at different wavelengths. A spectrophotometer passes light of known wavelength through a sample and detects the intensity of light transmitted. The difference between incident and transmitted light is used to calculate absorbance, which is directly related to the concentration of the analyte according to Beer-Lambert's law, which gives us the formula of A, absorbance, equals to molar absorptivity multiply concentration multiply path length. The objective of this experiment is to use spectrophotometry for qualitative and quantitative analysis of biological samples and molecules.
Here are the essential materials needed for this practical: spectrophotometer, cuvette, Bradford reagent, distilled water, test tube and test tube rack, micropipeters, 70% of ethanol solutions 1 mg per ml, BSA protein, standard unknown protein solutions A, B, and C.
For part 1 of the experiment, micropipetters were used to dispense 4 ml of distilled water in 6 test tubes. Then, 1 ml of Bradford reagent was added to each test tube. $50 microliters, 100 microliters and 200 microliters of BSA protein standard were prepared in duplicate and then added. The samples were read from the least concentrated and each absorbance was recorded. The sample without protein was used as the blank to zero the machine.
Before we could measure our unknown samples, we followed a standard preparation protocol, similar to the one used for the standard curve, but replacing the known protein with our unknowns. We began the preparation by dispensing the necessary amount of distilled water into our test tubes, followed by the addition of exactly 1 ml of the Bradford reagent into each tube. The core preparation involved using micropipettes to carefully add the unknown protein sample A, B, and C into the corresponding test tubes. Once the unknown protein solution mixed with the Bradford reagent, the solution immediately began to turn blue. We then used a vortex mixer to ensure the solutions was thoroughly and uniformly mixed. After vortexing and allowing the color to fully develop, the solution was carefully transferred into a clean cuvette. These prepared cuvettes, including the blank, were then transferred to the lab assistant for the final reading. Our lab assistant was responsible for blanking the spectrophotometer at 595 nanometers with a zero standard and then recording the absorbance readings for our unknown samples A, B, and C. These absorbance values were then used with the standard curve to estimate the final concentrations.
This table shows the absorbances of the different concentrations of bovine serum albumin BSA protein measured at 595 nanometer wavelength of the spectrophotometer. This graph shows the standard curve according to the Beer-Lambert's law, plotting the absorbance of solutions with known concentration from the previous table. The x-axis represents the volume of BSA protein and the y-axis represents the average absorbance. The dotted line shows the best fit linear trend line. The linear regression equations for the graph is given as y equal to 0.004x plus 0.0803 with the coefficient of determination r² value equal to 0.8622, suggesting a strong linear correlation between concentration and absorbance of samples.
This table shows the absorbance readings used to construct our standard curve, which is the foundation of our entire analysis. Our experiment is grounded in the Beer-Lambert's law, which states that absorbance is directly proportional to concentration. This principle is what gives us this perfect linear relationship, a straight line, when we plot the absorbance of our known protein standards against their concentration. The equation we obtained from the standard curve for protein assay, y equals to 0.02x, gives us key validation points, the slope, the y-intercept, and the r² value. The slope equals to 0.02, a non-zero positive slope confirming our assay was successful. It means the protein reacted with the Bradford reagent and is actively absorbing light at 595 nanometers. The value of 0.02 is a measure of the dye sensitivity to this protein. The y-intercept is 0, which is ideal. This proves that the spectrophotometer was properly blanked with the reagent solution, ensuring all measured absorbance is purely due to the protein. Our coefficient of determination, R-square, is a perfect 1.0. This tells us our standard solutions were prepared precisely and our readings were accurate, giving us maximum confidence in this line. We can now use our validated equation y equals to 0.02x to find the concentration of our unknown samples A, B, and C. We rearrange the equation to solve for x, our unknown concentration, by dividing the measured absorbance y by the slope 0.02. For example, unknown A had an absorbance of 0.0133. Substituting that value gives us x equals 0.133 divided by 0.02, resulting in a final concentration of 6.65 micrograms per milliliter. Following this process, we successfully estimated all three unknowns, finding that unknown B was the most concentrated sample at 8.85 micrograms per milliliter.
Our practical successfully introduced and applied spectrophotometry for both qualitative and quantitative analysis of proteins. The first part successfully demonstrated a linear relationship between the average absorbance and the increasing concentrations of the standard protein, which confirmed the validity of the Beer-Lambert law for this practical. Based on the part 1 result, a linear standard curve was generated. The resulting equation, approximately y equal to 0.02x, was used to accurately calculate the unknown concentrations. The final estimated protein concentrations for our unknown samples were unknown A, 6.65 microgram per milliliter, unknown B, 8.85 microgram per milliliter, and unknown C, 7.60 microgram per milliliter. In conclusion, the experiment successfully utilized the standard curve method to estimate unknown protein concentrations, demonstrating the reliability of the Bradford assay in biological quantification.